So on Friday, you learned chain rule without me, with a sub. How did that go? Okay. All right, so chain rule, when you're doing chain rule, you work a derivative outside in. The guts never, ever, ever, ever change, ever, right? Guts stay the guts, and then you multiply by the derivative of the guts, right? Okay, so the derivative of cosine of x squared minus 5, you're thinking the derivative of cosine, well, that's negative sine, so it'd be negative sine x squared minus 5. The guts don't change. And then you multiply by the derivative of the guts, which is 2x. So you end up with negative 2x sine of x squared minus 5, which walking around the room, yes. Not a single one of you guys simplified, but that's okay. Well done. All right, so I don't know why I have a hard time not putting the 2x in front. But okay, good. So everyone got A right. Well done. Letter B. So when you are doing a derivative of like guts to the 6, don't even think about what's in there. Just think guts to the 6. What's the derivative of guts to the 6? 6 times guts to the 5th, right? The guts don't change. Guts stay the guts. So you have 6 times guts to the 5th, and then you multiply by d guts. So the derivative of the guts would be 8x minus 3. So 6 guts to the 5th times 8x minus 3. Good. I think that, yeah. Perfect. 100%. We're 2 for 2. Woo! Okay. Letter C. The derivative of, think of it as sine guts, right? This isn't sine times cosine, it's sine of cosine. So the derivative of sine guts is cosine guts, right? So the derivative of sine is cosine of whatever's in there. In this case, it's cosine. Times the derivative of cosine, which is negative sine. So the derivative of sine of cosine of x is cosine of cosine of x times the derivative of cosine, which is negative sine. So no, you guys differentiated your guts, right? Never changed the guts. All right. So, okay, we're 0 for 1, but you guys got it. Well done. Ooh, okay. So this one letter killed you guys. So these guys wrote cosine x. They confused of with times, right? So it's not cosine x times cosine x, it's the cosine of cosine x, right? Which is not in any way cosine squared. So be very careful that you know the difference between cosine times and cosine of. So you guys got it, well done. Little warning, I'm doing a caution on every single board on this one. A little warning on this one. So when you put a dot for times and then you have negative sine x, just be careful because if you aren't, like if say you had to use this for another step, it's really easy to not see the dot and think of this as cosine of cosine minus sine x. So be very careful. That's why whenever I have a times negative, I would put this in parentheses just so I know it's not minus, it's times negative, which is different. Okay. But you got it right, so hold on. You guys got it? Beautiful. That's gorgeous. Look at that. Beautiful. And beautiful. Okay, so we had like over 50%, so that's good. You know. All right. So, and then the groups that missed it, I think you guys know what. Whoa, woo! Let's look at D. Just because it's big doesn't mean it's difficult. All right? So don't let the guts scare you. It's still guts to the third. What's the derivative of guts to the third? 3 times guts to the second. So the guts stay the same. So, all right, you guys, once you went here, then you guys went on this downward spiral of wanting to constantly integrate the guts. Don't do that, right? Okay. So be so careful. You have 3. Oh, no, you have 3. Yeah, you differentiate the guts. Okay. So don't differentiate your guts. Guts have to stay the same. Just think like when you differentiate, things get smaller and changed. If you don't want your, well, maybe you want them smaller, but you don't want them changed, right? You don't want anyone messing with your guts. So guts stay guts.
That's supposed to be a 3.
That is supposed to be a 3, not a 2? Oh, out front?
Yeah.
Okay. It just got partially erased. 3. All right. So anyway, so what we have is 3 times guts squared, right? So we start with 3. What are the guts? 1 plus 2x plus 1 to the 4th. Once you get that, you do like your outer derivative. Ignore the outer part and just look at the guts and just pretend this stuff isn't there and just look at the guts and think, all right, I just need to times now by the derivative of 1 plus 2x plus 1 to the 4th. So I'm multiplying by the derivative of 1 plus 2x plus 1 to the 4th. The derivative of 1, of course, is 0. The derivative of 2x plus 1 to the 4th, it's like its own little chain rule problem. 4 times 2x plus 1 to the 3rd times 2. All right, so gorgeous. Well done. Good. We're 2 for 2. Very nice. Well done. Oops. You guys did so much. What happened? Did you just keep on going? You're like, I'm just going to keep differentiating until it goes down to 0. Yeah. Okay. All right. Okay. Is this correct? Yeah, it's 4 times 2 times 3 is 24. Yes, this is correct. Oh, yeah, it's correct and simplified. Wow, that should be like a star. Right? Okay. Good. Most of you did great on this, and it's not an easy one. Okay. All right. So well done. Okay. Next one, cosine squared. Whenever you have a trig function raised to a power, I told you on the video, I don't know if you caught this, always rewrite it with the power on the outside, because then it helps you see chain rule so much better, right? It's a visual thing. So always put that power on the outside, and then you can see when that, oh my gosh, I got to do chain rule, right? So now my y prime, so it's just 2 times guts to the first times the derivative of cosine of 5x. Well, it's kind of like its own problem. The derivative of cosine of 5x would be negative sine 5x times 5. It had its own guts in there. These are nested chain rules. So you can have a chain rule embedded inside of a chain rule. So, and that's okay. It's like an f of g of h of x. Yes?
Why is it times 5?
So if I just gave you the problem, y equals cosine 5x with nothing else, and I said, what's the derivative? What would you do? You'd say, all right, derivative of cosine is negative sine, guts stay the same, right? Times the derivative of the guts, which is 5.
Got it.
Okay.
So it's another chain rule side of the chain.
Yes. Yes. I like to call them nested chain rules. They're embedded chain rules. It's a chain rule within a chain rule. So this last one has chain rule within a chain rule within a chain rule. It's like a triple nester. I'm going to delete this just so I have space. So that's the answer to this last one. Kind of curious if anybody. Let's see. You had the 15. You had the second, fourth. You had whoops. You have one mistake, and it's just this guy right there. You guys, I think, got it. You're this group right here. You've got your 15. You've got your sine to the fourth. You've got your cosine. What? You got it. Well done. Well done. All right. You guys know, but that's okay. This is a toughie. You guys didn't even do it. Right? Okay, you guys got close. You missed some stuff. Okay, same thing. You guys missed some stuff. Okay, so we had one group that got it, and then one group that was really close, but it didn't. Okay. All right, so let's walk through it. First thing we're going to do is I'm going to rewrite this as sine of tan of, I'm going to put the 3x in a parenthesis just to have it a little clearer, all right? Okay, so here we go. The first thing that we do, what's the first part of this derivative that I take care of? The fifth power, right? Outside. So I have 5 times the sine of the tan of 3x to the fourth. Now I look at, I just look at this part, and it's almost like this is its own problem, right? The outer stuff, I've taken care of it. Now I got to multiply by the derivative of the guts. So think of it as like sine stuff, or sine of guts, right? The derivative sine is cosine. So this would be times the cosine. Do the guts change? No. Cosine of the tan of 3x. There's the derivative of that part, but I got to do times the derivative of those guts. Derivative of tangent, of course, is secant squared. So we have secant squared of 3x, and then I got to do times the derivative of those guts, which is 3. So was that a quadruple chain rule? It was yeah. All right. And then you're done. So, all right. Good warm up. Today we are doing section 3.5, but it actually should say 3.5a. We spent 2 days on section 3.5. Today we're doing what's called implicit differentiation. I'm going to try to introduce implicit differentiation to you kind of slow, so to help make it stick. By the end of the day, you're going to love it. I really can't promise that, but hopefully you'll be able to do it. And if you can't do it by the end of the day, that's okay, because the test is not tomorrow. How many sections are in chapter 3? 10. There are 10 sections in chapter 3, and quite a few of them are split over multiple days. So this is a huge chapter. The next test is the week of MEA. We found out that the Wednesday, we had it scheduled for the Wednesday before MEA. So I don't know what MEA is, like the 18th or 17th or so, whatever those Thursday, Friday are. So we had it scheduled for that Wednesday before. And then we found out that that Wednesday is PSAT day. How many of you are taking the PSAT? Yeah. So we didn't want to test on a day when more than half of our students are out. So we decided to move the test to a Tuesday, which means part of my planning period today is going to be figuring out how to redesign the test a little bit. What we might do is do the essential learning portion, that little front part. We might do that on Monday, and that way we get Tuesday for the rest of the test. So 70 minutes for the rest of the test. So anyway, that's what we're trying to work out. But it's going to be, so you got another couple weeks before that test. Okay, I am going to cover this up with a shield for a moment. All right, in your groups, here's what we have. We have explicit, y equals negative 3x plus 5, and we have implicit, 3x plus y equals 5. In your groups, I want you to take 30 seconds and decide what you think the words explicit and implicit mean based on this. Go.
Well, it's probably directly saying the slope versus the line.
You're right. But that's like, so for example,
All right, this group. What do you guys think explicit means?
That like y, like one variable or one function is equal to everything else. It's not like separated or not separated. It is separated.
Okay, so what I think I'm hearing you say is you have isolated one of the variables.
Yes.
Okay. Would it matter if I had x equals? Would that also be explicitly defined then?
If you're trying to find the yes.
Okay, all right, that's fair. A different group, what do you guys think? So middle group, what do you guys think implicit means? You.
if you have two variables on one side.
Okay, all right. Those are both very reasonable based on what we saw. Did anyone come up with any type of a difference description? In standard form. Okay, yeah, I hear that a lot. Very good, and that's true, right? It's not the definition, but it is an action. Based on this, it's a true assessment of what we've got here, right? Okay, so technically, you guys are close. All right, so it has to be solved. One variable needs to be isolated, but the variable needs to be what's called the dependent variable. So the output, right? Has to be solved for the output variable. So an explicitly defined function, I'm just going to write in simple lingo, just means it's solved for y. Okay, and an implicitly defined function, in fancy talk, means not solved for y. Okay. So I want you all to do something for me. On your paper, I want you to write this equation right here. Y equals negative 3x plus 5. Just write it on your paper. Below it, I want you to write the derivative. Tommy, what'd you get for the derivative? Good. Thank you, Tommy. So just have all you have on your paper is negative 3. Do you have anything on this side?
No.
Y prime. You gave it a name, right? Okay. Does everyone have pretty much the same thing? Did anyone call it something different? No one used dy dx? You all used y prime? Why?
It's quicker.
Because it's faster. Okay, that's fair. Okay. So here's the thing about derivatives. Differentiation is an operation like addition, subtraction, multiplication, division, differentiation. You have learned a new operation. It's considered a mathematical operation just like any of the other mathematical operations you have learned. Yeah. Okay, took you a while to get there, right? Yeah. Okay, but you're there. So here's the thing. If I have an equation, can I just like add 3 to the left and have a good equation? What do I have to do if I do something to an equation? I gotta do it to both sides, right? You have to do it to both sides. So if we have the equation y equals negative 3x plus 5, you can't just take the derivative of the right side and not take the derivative of the left side. So what you guys have been doing all along is you think that that y prime is just the name of your answer. It's not. That's the derivative of the left-hand side. So what you've been doing all along is you've been differentiating both sides. It's just that every function we gave you was explicitly defined, so the derivative of y was always just y prime, or dy dx, right? Okay, are you following me a little bit? Yes, okay, good. Oh, you guys are thinking ahead. Okay, don't go too far ahead. All right, gotta stay with, this is a big subject, so you gotta kind of stay with me a little bit. So the derivative of y is y prime. The derivative of negative 3x plus 5 is negative 3. Because we have done the same operation to both sides, our equation is still in balance. Now, let's go over to this guy. So go ahead and take, write this on your paper. 3x plus y equals 5. If you don't already have it written. Let's write underneath it. We're going to do this together. What's the derivative of 3x? 3. What's the derivative of y? Y prime. And what's the derivative of 5? 0. So if I wanted to solve this for y prime, I get the same thing, right? I just differentiated it. It just looked a little different when I started, right? This is called implicit differentiation. So this is what you've been doing so far, explicit differentiation, when it's already solved for the dependent variable. But now today, we're going to hit all these functions that aren't, and you're going to learn how to differentiate them implicitly. Now there's a lot more to it than this. But the main thing, if you learn nothing else, if you learn the derivative of y is y prime, that's a big deal, right? However, I'm not going to let you call it y prime. Starting from this moment forward, now you can use y prime in general, like if we're doing stuff, and it's not, I won't take off if you don't call it y prime, but there are 3 really important reasons that I say not to use y prime, all right? So instead of y prime, what's another name for the derivative of y? dy dx. And that's what I want you to call it. 3 reasons why. One reason might not affect you. It affects me. Those of us who have messy handwriting. How many in the room have messy handwriting? Okay. If you have messy handwriting, it's really easy to get your y's and your y primes mixed up. And in these equations, as they get more complicated, you're going to have y's and y primes flying all over the place. So dy dx, you won't get dy dx mixed up with a y. So it's easier just from a clarity standpoint to make sure that your work is clear. All right, so that's number 1. Number 2, not today, not tomorrow, not at all in this unit, but sometime in the next couple months, we're going to learn a concept called differential equations. And when we learn a concept called differential equations, which goes kind of hand in hand with this, it's just that you have to learn a bunch of other stuff first before you can learn that. This is just like the beginning of the steps to this new topic. It has to be dy dx because you're going to pull them apart. Believe it or not, dy dx is a real fraction. You could, don't write this down on your paper because then you just freak out, right? But you could, like this and this are saying the exact same thing, right? You can take the dx and multiply it to the other side. So, so anyway, that's what we're going to be doing in a little bit, like maybe a month and a half from now, is we're going to be ripping those dy dx's apart and then sticking them on sides and doing stuff with them. So, but you can't do it if it's a y prime, right? Okay. And the other part that affects you the most today is we don't always differentiate with respect to x. So if I asked you to differentiate with respect to q, it wouldn't be a dy dx. It'd be a dy dq. And it's important to know what you're differentiating with respect to. You can differentiate with respect to q even if there's no q's in your equation at all. So we're going to get into, Vishal is like, yeah. So you can differentiate to any variable you want. It doesn't have to, you don't have to see it to be able to do it. Remember, a derivative gives you what? Slope. What else have we called it? What else would you describe a derivative as? Instantaneous rate of change, right? If y represents, I don't know, like say y represents my weight, all right? Let's just go there. All right, so if y represents my weight, right? Let's say x represents my height. So I could say, all right, what is the rate of change of my weight with respect to how tall I am, right? So as I get taller, my weight probably gets bigger, right? It's the rate of change of my weight with respect to how tall I am, right? But I don't have to do it with respect to how tall I am. I could do the rate of change of my weight with respect to time, right? As time goes by, how is my weight changing, right? My height might not change at all, but my weight sure might change much, right? So, so I could do it with respect to time. I could do it with respect to my shoe size, right? As my feet get bigger, like when my feet were growing, how was my weight changing, right? One might not affect the other, but you know there might be a relation there. So we're doing statistics, a correlation, right? Not necessarily causation. So anyway, but you can still have a correlation, right? So anyway, so the variable, like what you're differentiating with respect to, you can differentiate with respect to a whole bunch of different things. And it still has meaning. It's just different meanings depending on what you're finding that rate for, right? So anyway, all right. So that being said, so that's why I like to have a dy dx, because then we know what we're differentiating with respect to. Yes?
So how did Newton do the like multiply dx other side?
Yeah, I don't know. I've never actually read his, what is it, Principia Mathematica? Like, I never read it to know exactly what was the calculus that he was studying versus Leibniz. They both, we're going to talk about that today, but it's considered that they both kind of discovered calculus independently, and they both focused on different things. Newton really didn't focus that much on integral calculus. He focused more on what's called differential calculus, whereas Leibniz did more with integrals. And so the splitting apart you only need to do when you're doing integral kind of stuff. So maybe it just never came up, right? Newton was big on rates. Like he really was big, like, okay, Newton, what was his big thing? The laws of thermodynamics? Is it thermodynamics that were Newton's, right? But he was big on motion, especially motion that was non-constant, and even motions of things that like things over other things, like wave kind of motions and like fluid dynamic kind of motions, right? That was Newton's big thing, which is all, differential calculus. So that was his big thing. Whereas Leibniz is a whole different world of stuff. So I don't remember what Leibniz, if he had any big applications that I'm sure he did. But what was he focusing on? But anyway, yeah, Newton is our mathematician today. So we're going to talk about it. All right, so anyway, that being said, oh wow, we're still on screen one. Okay, so anyway, this whole thing was just to get you to understand that the derivative of y with respect to x is dy dx. So think of it as like d dx of y, so the derivative of y, is dy dx. So whenever you need to differentiate a y, if you're doing it with respect to x, you would write dy dx. Okay. All right. I'll give you, some people are writing that. You don't have to write everything, but all right. We're going to skip the next slide and come back to it. While you're writing, I'm going to tell you, implicit differentiation is really hard to say in words. It's easy to learn. Once you get the basics, you'll fly through these. But it's really hard to say in words. This is the gist of what you need to learn today. Whenever we differentiate a variable that is not the indicated independent variable, which, in other words, the variable with which we are differentiating with respect to, we must multiply by the differential, in other words, the derivative of this new variable. So that's what you got to learn today. Those are big words for a fairly simple concept. It's just hard to put it into words. So here's the thing. Here's what it says. If you're finding dy dx and you hit a variable that's not x, you got to multiply by a differential. That's what it means. So if I'm finding dy dt and I hit a variable that's not t, I got to multiply by a differential. Whenever you hit a variable that's not the variable you're differentiating with respect to, you're going to have to multiply your derivative by a differential. What's a differential? Technically, a dy, that's a differential. A dx, that's a differential. We tend to just kind of dy dx, we just call it a different, technically they're differentials, just call it a differential. It's okay. It's just kind of a, that's what we call that, those d's. So anyway, we're going to go back. I'm going to walk you through this, and then we're going to go back to that page and explain it some more. So we're going to walk through this problem together really slow. I'm going to rewrite it here so you can see. Hey, what does the graph of this look like? There's a circle. What's the radius? 5. Good. What's the center?
0 to 0.
The origin. Very good. Okay. Just checking your algebra there. All right. So we're going to find dy dx. What are we differentiating with respect to? X. So the first term here, this x squared, do I have to multiply by a differential? No, because the x matches the x. And if they match, I'm good. I'll show you why in a minute. Don't worry about the why. Just right now, let's just do nuts and bolts. All right. So what is the derivative of x squared? 2x. All right. Now I've hit a y squared. Is y the same as x? No. So now for this guy, you got to multiply by a differential. But first, before you do that, you got to find the actual derivative. So you do the derivative of y squared just like the derivative of x squared. So if the derivative of x squared is 2x, what's the derivative of y squared? 2y. The difference is that we have to multiply this guy by the derivative of y, which is dy dx. What's the derivative of 25? 0. All right, everyone take 10 seconds and solve this for dy dx. It's okay to have x's and y's in your answer. Is that okay? Good. So now let's go ahead and do part B. Part B says, find an equation of the line tangent to the circle at the point 3, 4. What two things do we need for a tangent line? Okay, we need a slope and we need a point. Do we have a point? Yes, it's 3, 4. So now we need a slope. What gives a slope? The derivative, right? So for our slope, we're going to use our dy dx. Now, I'm going to use fancy notation here. You don't have to. You could just write dy dx equals. I'm going to write dy dx evaluated at the point 3, 4 is. So I'm going to plug the point 3, 4 into my dy dx. Notice when I plug in, I have to use both the x and the y. So what's my slope? Negative 3/4. So my equation, y minus 4 equals negative 3/4 times x minus 3. Done. All right. Now, let's learn why we have to multiply this guy by a differential and not this guy. So, suppose f of x equals y. So y is f of x. Think of this as like y, not y prime, but think of this as like y to the first power. Okay? So, if I do chain rule says the derivative of y to the first is 1 times y to the 0 times the derivative of the guts. But what is the derivative of y with respect to x? dy dx. dy dx. So this is just a big giant fancy talk for f prime equals dy dx, or the derivative of y is dy dx. Let's take it up a notch. Suppose f of x equals y cubed. I'm going to put the y in parentheses. Okay, so derivative of f of x is f prime of x. The derivative of y cubed, well, that would be 3y squared times the derivative of y with respect to x, which is dy dx. So you end up with 3y squared dy dx. Anytime your guts are a variable that's not the x, whenever you do your d guts, which you have to do every time, it's going to be that differential. It's going to be dy dx. So why don't we have to do it for x? Suppose f of x equals x cubed. So our f prime would be 3x squared times the derivative of x with respect to x. What's the derivative of x with respect to x? 1. It's dx dx, right? The derivative of x with respect to x. Right? This is what you're differentiating. This is what you're differentiating with respect to. Right? The derivative of x with respect to x. But what is dx dx? That's just 1, right? So when your variable matches the variable you're differentiating with respect to, you don't have to write the differential because it will always be 1, because it's always going to be that over itself. So, yes?
Is the bottom number the one you have to respect to?
Yes, yes. So like when you have, so this would just be 3x squared. So let's just write this. So this is the variable I am differentiating. Sorry, it's big words, but there's really no good way to avoid it. Variable I'm differentiating. Variable I am differentiating. I'm going to abbreviate differentiating with respect to. This is what what I'm taking the derivative of, and this is what it's with respect to. Top is what you're differentiating, bottom is the with respect to. All right. So, for example, now we're going to move on because we're going to do this in one of the next examples. I'm not going to go back. We're going to go forward. Let's move forward. Okay, but I'm going to give people one more minute. Okay, so don't do this. We'll do it, but not yet. Let's start small. All right. Here we go. So this first one, I'm going to walk you through. We're going to do this in multiple parts. So we're going to have an A part 1, a B part 1, and then an A part 2, and a B part 2. I'm going to walk you through the A part 1. You're going to do the B part 1. Then I'll walk you through the A part 2, and you're going to do the B part 2. So A part 1, I want you to just differentiate this with respect to x. So on the left side, we have 3y squared. We're differentiating with respect to x. What is the derivative of, first, just what's the derivative of 3y squared? 6y, and then I have to multiply it by dy dx. On the right, what's the derivative of 4x? 4. Do I have to multiply it by dx dx? No, I can, because that would just be 1. Then you solve for dy dx. It's 4 over 6y. So that's the one I'm going to do. You guys are going to do this one. So take a minute and give it a try. I'm going to walk around and pause this. The derivative of 8x to the 5th.
40x to the 4th.
Good. Oh, we're all good on that. 40x to the 4th. Good. This is a guts kind of a thing. It's a chain rule. So we have negative 21. Do the guts change?
No.
No. 2y minus 4 to the 2nd. Now we're multiplying by the derivative of 2y minus 4. But we're differentiating with respect to x, right? Since the y doesn't match the x, we're going to have to multiply by the differential. So the derivative of 2y minus 4 is 2 times dy dx. And this whole thing equals what? 0. Don't forget the 8 goes to 0. All right. To solve for dy dx, move any term that doesn't have a dy dx to the other side. So we have, I'm going to do 21 times 2. So I have negative 42 times 2y minus 4 squared times dy dx equals negative 40x to the 4th. And I'm just going to kill the negatives, right? Okay, so it's this times this equals this. So I'm going to have to divide, right? So dy dx equals 40x to the 4th over 42 times 2y minus 4 squared. Any questions on that one? We're all good? All right, good. Let's do letter A subpart 2. We're going to do the same problem, but now we're going to differentiate with respect to t. Are there any t's in here? Nope, but that's okay. So for letter A, subpart 2, so we start with the derivative of 3y squared. I'll give you a minute. What's the derivative of 3y squared? 6y. And then we have to multiply by the differential, which would be dy dt. It's what you're differentiating over what you're differentiating with respect to. 6y dy dt equals, what's the derivative of 4x? 4. Do I have to multiply by a differential?
Yeah.
Yes. What would that be? dx dt. It's what you're differentiating, which is x, over what you're differentiating with respect to, which is t. Right? Nothing to solve for, because it's not like one wins over the other. So you just kind of leave it like that. All right, so everyone try letter B, subpart 2. Differentiate this thing with respect to t. You don't have to solve for anything.
You just leave the first answer at that.
Yep. Yep.
might want to pause the recording.
Oh, thank you. Tommy, pay attention to what variable you're differentiating when you write your differential. All right, here's my, there we go. All right, so for this one, the derivative of 8x to the 5th, 4x to the 4th times what? dx dt. What you're differentiating over what you're differentiating with respect to. All right, the derivative of negative 7 times 2y minus 4 to the 3rd is negative 21. Guts stay the same, times 2y minus 4 to the 2nd. D guts, the derivative of 2y is 2 dy dt. The letter you're differentiating over the letter you're differentiating with respect to. And then what does this all equal? 0. And then you can just stop. Any questions on this? Are you starting to get the feel for it? Okay, good. All right, we're going to take 1 minute and do this one quickly. So write this one down, and then I'm going to give you 1 minute to find dy dx. So first, just do the first line. So write the problem down, and then just do your first line that you would write for your derivative. Bless you. Once you get your first line, check with your neighbors. See if you match. You match? Good. All right, let's see if I match. So we're differentiating with respect to what variable? X. So for x squared, what's the derivative? 2x. Do I have to write a differential? No. So derivative of 2y cubed. 6y squared, do I have to multiply by a differential?
Yes.
What is it?
dy dx.
dy dx. Yep, every time you differentiate a y. So derivative of 4y would be 4 dy dx. And what about the number 2? 0. Good. Any questions on that? All right. Oh, yes.
So when you put the UIDX
Every time you differentiate a variable, and it's not the variable you're differentiating with respect to.
okay.
That's hard to say in simple words. So anytime the letter you're differentiating doesn't match the bottom there. Okay, how do we solve for dy dx when it's in multiple terms? Yes?
You take it out of, I assume you could take it out of
Okay, you're on the right track. So before we start doing our favorite F word, which I'm hearing, right? Before we start doing that, first thing you want to do is move all the other terms to the other side. So move anything that doesn't have a dy dx in it to the other side of the equation. All right, Ian, what's your favorite F word? It is factor, isn't it? Yes, okay. So we're going to factor a dy dx out of both of these terms. Oh, yeah, R is just ready to say the next step, and then we divide, right? So once you factor, then you divide. By the way, this is fine. If it was a multiple choice, and I gave you that answer, would that also be correct?
Yes.
Yes. because you're multiplying top and bottom by -1, right? So you'll see a lot of times the College Board doesn't like to have leading negatives, so they'll clean it up. Okay. All right. Okay, taking it up a little notch. The first term is 3xy cubed. What rule does that term require? Product rule. So here's how I like to think of it. When I have a leading coefficient on a product rule, I kind of stick it with the first part of the first term. So I would think of this as 3x times y cubed. Right? So give this a try. Again, it's a dy dx. That's the f prime g. Well done.
3 1 cube plus 3y squared.
Oh, wait. Oh, why was it there? Okay.
Oh, yeah.
It's just wrong. All right.
We're not
Oh, yeah. Oh, it really wasn't that bad. You did your y first.
Yeah, we're doing bottom right.
What's the derivative of 3x? 3. Okay, whoops. Good. Times y cubed. Do I have to multiply by a differential when I differentiate 3x? No. So then plus 3x times, what's the derivative of y cubed?
3y squared.
3y squared. Now dy dx. Okay. Minus 2 times dy dx equals 0. You do not write a dy dx every single time you write the letter y. The only time you multiply by the differential is if you're differentiating the letter y, right? So if you didn't actually take the derivative of a y, like on this first term, we were differentiating 3x, right? So we don't have a differential for this term. Okay, does everyone understand that?
Yeah.
All right, so now to solve, did you all solve?
Yeah.
Okay, so you move the 3y cubed over and then you factor out a dy dx and you get negative 3y cubed over 9xy. Oops, x, that's a y. My brain got ahead of my head. Okay. 9xy squared minus 2. All right. Yay. We're getting there. All right. Try one with respect to t. You don't have to solve for anything. All right, what's the derivative of y squared?
Is it 2y dy dt?
Yes, it is. Good. Nahika, what's the derivative of 5x? You're so close. It's 5 and the dt is right, but what is the letter we're differentiating? Good. Good. Does everyone understand why it's dx dt? Yes. Good. All right. The next screen, we're not going to have time to do 14 practice examples, and the bell's going to ring in just a minute, but just for fun, so what's d theta of 3x? Whoa.
3 dx theta.
D theta. Good. What's d theta of 3 theta?
3.
It's just 3. No differential?
No.
No. Good. What is okay. d theta of xy squared? Walk me through. Derivative of x is 1 times
2
Y squared.
okay. Times y squared times derivative of x is dx d theta times y squared plus
y
d theta. I think the evilest question on this screen is this one.
It's dx y.
So it'd be 1 dx dy times y squared plus
X plus
x times
2y.
2y. No differential for the y?
No.
Why not?
Because it's dy.
Because it's with respect to y. Okay. All right. Good. Okay. Wonderful work today. I know it was a hard day, but it's a good working day. Tomorrow we should be able to have a slightly shorter lesson and then be able to work on those quizzes a little bit more.